Okay, so let us continue our discussion on electroosmosis. We told that if you have a charged surface and there is an ionic liquid in contact with the charged surface, then we form a electrical double layer, and by applying a voltage difference between the two ends of a uh, capillary, for example, we will be able to drive the fluid. Okay, so we can create pumping action in doing so. Okay, and so what would happen is closer to the wall we would create a diffuse layer, and if the wall is negatively charged we would create a positive charge rich region in the diffuse layer, and if you create an electric field, this the liquid the charges in the liquid in the diffuse layer, they will tend to migrate towards the cathode, and in doing so they will carry the bulk of the liquid with it because of the viscous drag. Okay. So if you look at the Navier-Stokes equation, what happens is you have rho into del V over del T plus V dot del V is equal to minus gradient of pressure plus del square V, that is the viscous term, minus electrical charge density into the gradient of potential. Okay. So this is the electrical body force term. Okay. So this electrical body force term basically accounts for the force exerted on the fluid because of the electric field. Okay. So if you were to solve a case where we would talk about how the electroosmotic velocity is going to look like, then we would have to consider the Navier-Stokes equation, and we have to include this electrical force as a body force term in the Navier-Stokes equation. Okay. So let us look at a simple case, flow between two infinitely long parallel plates, and we apply the appropriate boundary conditions to derive the expression for the velocity profile. Okay. So we look at ideal electroosmotic flow between parallel plates. Okay. So there are some assumptions that we would make here. We would make some assumptions. So the assumption is that the external electric field does not change the charge distribution, the charge density. Okay. So we assume that the charge density inside the liquid is because of the charge distribution that happens when the liquid, ionic liquid, is in contact with a charged surface. Okay. And the external electric field does not create any charge, so there is no change in the charge density. Here we consider ideal electroosmotic flow, meaning there is no external pressure gradient present here. Okay. So we also say that no external pressure gradient. Okay. So with those two assumptions, if you look at the situation, this is the situation. We have two infinitely long parallel plates. So this is the bottom plate, okay, and this is the top plate. Okay. And so we, because these surfaces are charged surfaces, okay, So, in this case the surface is positively charged. Okay. So, we have the positive terminal there, negative terminal there. Since the surface is positively charged, we would have a negative charge region in the electrical double layer here. Okay. So, across this electrical double layer we would have a charge a negative charge rich region. So, when we apply an electric field, these negative charges would try to migrate towards the anode. So, thus it will create a velocity in this direction, okay, in the positive x direction. So, and here we say that there is no external pressure gradient. So, P external at x equal to 0 is 0 and P external at x equal to L is 0 and the potential on the left hand side is 0 and on the right hand side is delta V. Okay. So, we talk about here, so here we talk about infinite parallel plate channel, okay, and the charged walls are located at z equal to plus minus h by 2. So, we say that the center is here at the middle between the two plates. So, at plus minus h by 2 we have the charged walls, okay, and the assumption that external pressure gradient is 0, external pressure gradient is 0 and the external electric field is in the negative z direction, because we have delta V here and 0 here. The direction of the electric field is in the negative x direction. Okay. So, external electric field in negative x direction. Okay. So, we can write electric field E as negative E into Ex. This is the unit vector. So, it means that the electric field is in the negative x direction, and we know that the gradient of the electric potential del phi r equal to negative of electric field. So, it will be E into Ex. Okay. Now, the pressure gradient del gradient of external pressure is 0 and the velocity Vr is only in the x direction and it varies across z. Okay. So, the velocity is going to be only in the x direction and it only varies in the z direction, right. So, that is what this means. We can write the Maxwell's equation for the electrical charge density, which is given by electrical charge density equal to minus epsilon into del square phi r. Okay. So, with that if we write the x component of Navier-Stokes equation, x component of Navier-Stokes equation, then I can write rho into del E over del T plus U dot del U equal to minus del p over del x plus eta del square u minus electrical charge density into the potential gradient. Okay. So, we are talking about steady flow. So, this is 0 because we talk about steady flow, and this is the acceleration term which is 0 because we are talking about uniform flow there, and no pressure gradient. So, this term also vanishes. So, we have only these two terms in the equation. Okay. So, we say that eta del square u over del z square, because u is only a function of z, and we have an expression for the charge density from here. Okay. So, we can write plus epsilon del square phi z divided by del z square into electric field is going to be 0. Okay. So, now we can integrate, we can say if we take this to the other side of the equation and integrate, we get minus eta into uz will be equal to epsilon into phi z into electric field plus C1z plus C2. Okay. So, that is the equation we get. Now, what are the boundary conditions we have? The boundary conditions, one is the no slip boundary conditions, that means the velocity at plus minus h by 2 at the plate, okay, will be 0, and the other condition is that the gradient of the velocity as we move away from the wall, okay, as I said in the bulk there are equal number of positive and negative charges, the velocity profile is flatter in the bulk liquid. So, the gradient of the velocity as z tends to infinity will vanish. Okay. So, we have two boundary conditions, one is the no slip boundary condition. So, one is the no slip boundary condition, we said u plus minus h by 2 is 0, and the second condition is del u over del z, z tends to infinity equal to 0. Okay. Now, if you apply this second condition on this equation for the velocity profile, we would see that the C1 has to be 0, otherwise it is not possible to evaluate this equation. Okay. So, to satisfy this, you see that the C1 constant C1 has to be 0, right. So, now if we apply the no slip condition, we have uz equal to minus epsilon phi into electric field over eta minus C2 over eta, right. So, if you say 0, so this is 0 at plus minus h by 2 equal to minus epsilon eta E into xi. So, at the wall this potential is going to be the zeta potential. Okay. So, divided by eta minus C2 by eta. So, we get an expression for the constant C2, C2 will be minus epsilon into electric field into eta, right. So, with that we can write down the expression for the velocity profile, uz equal to zeta potential minus phi z into epsilon E over eta. Okay. So, this is the expression for the velocity profile in case of flow through two infinitely long parallel plates. So, it depends on the zeta potential. Okay. Higher the zeta potential, the velocity magnitude will be higher, and it also depends on the electric field, is directly proportional to the electric field as well as the permittivity of the liquid, and it is inversely proportional to the viscosity. Okay. Now, if we go for the Debye-Huckle limit, where we say that the electrical energy is small compared to the thermal energy, okay, where the lambda d, the Debye length, is very small compared to the length scale bit of the flow that we are talking about, then we see what happens. Okay. So, under Debye-Huckle limit, which is nothing but thin electrical double layer, we have derived this in the earlier, del square phi over del z square is 1 over lambda d square into phi. So, this equation we derived earlier in case of thin electrical double layer limit. So, for the infinite parallel plate channel, infinite parallel plate channel, the surfaces are at plus minus h by 2. Okay. So, the potential at plus minus h by 2 is going to be zeta potential. Now, with this boundary condition, if we solve this, we get an expression for potential. Okay. We get an expression phi as a function of z, we get is zeta into cos hyperbolic z plus lambda d. This is what we had seen earlier. Okay. Cos hyperbolic h by 2 lambda d. Okay. So, this is the expression for the potential within the Debye layer. Okay. Now, if we substitute this phi z in this velocity expression, we have an expression for the velocity along z direction. So, we can have u z equal to 1 minus cos hyperbolic z over lambda d divided by cos hyperbolic h over 2 lambda d into a factor called, so you will have epsilon xi e over eta. Now, this is known as ideal electroosmotic velocity, ideal electroosmotic velocity u come a subscript EO. Okay. So, so if we assume that lambda d is less than h, which is nothing but the thin ideal approximation, then in that case you see that this term will be infinite, at the bottom will be infinite, this term will be 0. Okay, this complete term will vanish. So, u z will be equal to ideal electroosmotic flow, which is nothing but epsilon xi e over eta. Okay. So, this something we can tell when the electrical double layer is very thin as compared to the transverse length scale. Okay. Some typical values are the xi can be of the order of 100 millivolts, and we can define a parameter called electroosmotic mobility. Okay. So, we can define a parameter called electroosmotic mobility, which is the ratio between the ideal electroosmotic velocity divided by the electric field. Okay. And this is given by the symbol mu subscript EO. So, this is the electroosmotic mobility, okay, which is nothing but you can write this also as epsilon xi over eta. Okay. So, and typically this electroosmotic mobility mu EO is about 7 into 10 to the power minus 8 meter square per volt second. Okay. Now, if we use these typical values of zeta potential and electroosmotic mobility, the typical electroosmotic flow velocity is of the order of 1 millimeter per second. Okay. So, in a typical electroosmotic pumping, we can expect the electroosmotic velocity is of the order of few millimeter per second. Okay. So, now we talk about the flow rate. Okay, how knowing the velocity profile, okay, knowing the velocity profile or the ideal electroosmotic velocity, how we can calculate the flow rate. So, let us calculate the ideal electroosmotic flow rate. Okay. QEO is 0 to W. So, that is W is the width into the plate, okay, into dy, and then integration minus h by 2 to h by 2 dz, and the velocity is varying along z, okay, uz. So, if we do that, if we say that uz can be approximated as UEO, ideal electroosmotic velocity, then we can find an expression for the flow rate, which is UEO into WH, and so QEO is UEO into WH, and this is at lambda d less than h by 2. Okay. So, this is the expression for the velocity profile and the total flow rate in case of a flow through two parallel plates. Now, let us look at flow in a cylindrical tube situation. Okay. So, let us look at flow in a cylindrical tube or channel. So, for cylindrical channel, if you solve the the equation del square phi, if you solve this equation del square phi r equal to 1 over lambda d square phi r, solve for cylindrical channel, you get an expression for the potential phi r as this. So, xi I0 r over lambda d divided by I0 a over lambda d. Okay. So, this is the expression for the potential in case of flow in a cylindrical channel. So, this is how the potential is going to vary along the radial direction, where I0 is the Bessel function of first kind. Okay. So, there are I0, I1, I2 like that. So, I0 is the Bessel function of first kind. So, and V you can write is a function of R, but in the x direction. So, this is the velocity is in the axial direction. Then we can write down the boundary conditions. So, we have no slip boundary condition, which is the velocity at r equal to a, okay, at the perimeter is going to be 0, and the second boundary condition is that when you are talking about flow through a tube, we are talking about symmetry. Okay. So, the gradient of the velocity at r equal to 0 should also vanish. Okay. So, the gradient of del u over del r at r equal to 0 should also be 0, and this is the symmetry boundary condition. Okay. Now, using these two boundary conditions, if you solve the velocity profile, similar to this flow between flat plate case, okay, we have would have an equivalent equation in the radial coordinate, and if you solve that, so if you solve that for flow through tube, then you would get UR 1 minus I0 r over lambda d I0 a over lambda d into u. Okay. So, this is the ideal electroosmotic flow velocity. So, we can find the ideal electroosmotic flow rate, ideal electroosmotic flow rate So, we can write Q EO will be equal to integration 0 to 2 pi d theta 0 to a dr r u r theta, right. So, that is equal to u e o. If we, so this is basically going to be independent of theta. So, we have only as a function of r, you have a function of r. So, that is from here. Now, if we impose the condition that lambda d is less than a, then u r would become u e o. Okay. So, under that condition we can integrate this to get u e o into pi a square. Okay. So, the flow rate, electroosmotic flow rate equal to u e o into the area of cross section. Okay. So, now let us talk about Debye layer overlap. We have been talking about cases, we derived the expression for the velocity and flow rate for two different cases, one for flow between parallel plates, the second one is flow in a circular tube. And in all these different cases, we have been considering that the lambda d is very small compared to the radius of the length scale of the flow, but when the lambda d becomes comparable to the length scale, how the profile of the electroosmotic flow is going to change. Okay. So, that is something we can look at here. So, we look at Debye layer overlap. Okay. So, we talk about different length scale. In one case we have lambda d over A. So, let us talk about flow through a tube. If this is equal to 0.01, so that means we are talking about a tube of radius about 1 micron. Okay. So, micron size tube. So, this results in a flat profile. Okay. As you can see here, this is the value of lambda d over A, for which this is the flow profile. Okay. You can see that this is the radial velocity over this characteristic velocity, which is nothing but uEO, okay, at the center. So, you can see that the profile takes a much flatter. Okay. The profile is very flat at the significant part of the flow, okay, is flat. Now, if you take a value which is about 0.1, okay, so you are talking about a tube radius about 100 nanometer, okay, because lambda d is of the order of 10 nanometer. Okay. So, that is what we have seen earlier. So, radius is about 100 nanometer, then we see that the profile is parabolic, somewhat close to the walls, and towards the center it becomes flat. Okay. So, here we see that a rounded profile, but it is flat near center. Okay. Now, if we go to lambda d over A as 1, that means we talk about a tube of radius 10 nanometer. This is what we see. Okay. This is the velocity profile. Okay. So, the profile is almost parabolic, similar to the profile that we see in case of pressure driven flows. Okay. So, here the flow is parabolic. Okay. So, we see a parabolic profile. Okay. Now, if we write down the equation for the velocity ur is 1 minus I0 r over lambda d divided by I0 a over lambda d, okay, into u e o. So, this should be okay into u e o. Now, if we do a Taylor expansion of this equation, okay, and we have to learn how to expand when you have this Bessel function here. Okay. So, you can write u r to be s square over 4 lambda d square into 1 minus r square over s square into electrostatic velocity plus some terms which are of the order of a over lambda d square. Okay. So, this the order of. Okay. Now, here you can see as lambda d becomes comparable to the radius, okay. So the velocity is going to be you know suppressed, okay. So the electroosmotic flow is going to be suppressed. So as lambda d increases, the electroosmotic flow gets suppressed, okay. So that is what we also see here, okay. So here if you see on the x axis you have the lambda d over A, and the y axis you have the maximum velocity at the center divided by some characteristic velocity, okay. Now as lambda d over A, so if it is small, okay, when the lambda d is somewhere here, you can see that the velocity is comparable to the ideal electroosmotic flow velocity, and as lambda d over A increases, as the Debye length becomes larger and larger, the about let us say 1, this electroosmotic flow is heavily suppressed. So the actual velocity at the center is only 10% of the ideal electroosmotic velocity, okay. So what we learn is that the electroosmotic flow becomes beneficial only at the limit of low lambda d, or when the electrical double layer thickness is very small, okay. So here we have been looking at electroosmotic flow when the pressure gradient is not present, okay. But in most of the practical situations you always have a pressure gradient present which opposes the electroosmotic flow. When we have such pressure gradient present, the velocity profile itself is going to get modified. So we will like to see how it is going to get modified. So we look at pressure driven flow, we look at electroosmotic flow with back pressure, okay. So the situation we see it here, this is the situation, okay. So this is a circular capillary, this is a circular capillary. So we have this Debye layer here, okay, and we have positive there, negative there, and we say that the wall is positively charged. So we have negative charge rich region in the Debye layer which migrate towards the anode. So we create a motion in this direction, okay. But we have a back pressure that is acting because of the finite fluidic resistance, a back pressure acting. So we can see that the P external at x equal to 0 is 0, but the pressure at x equal to L is delta P. So we have some back pressure which is acting in this direction. The potential here is 0 and the potential here is delta V, okay. So here what we are going to predict is that the velocity is going to be we will see when we work with the Navier-Stokes equation, we will end up with a linear equation where we can find out the electroosmotic velocity and velocity due to the pressure gradient independently, adverse pressure gradient. So we can find the net velocity by adding these two together in a vector sense, okay. So let us look at so here we are talking about external pressure gradient is present, Okay. So, the conditions are phi at x equal to 0 is going to be 0 and phi at x equal to L is going to be delta V. The pressure at x equal to 0 is going to be 0 and the pressure at x equal to L is going to be delta P. Okay. Now, we can write, let us say we can write the potential negative gradient of the potential phi is nothing but the electric field, okay, and which can be written as minus delta V over L, okay, into E x. This is the unit vector, okay. So, and similarly we can write gradient of pressure is going to be minus delta P over L along x direction. So, this unit vectors represent this along x direction, okay. So, here we say that the velocity is along x direction and it varies in the radial direction. So, into E x, okay. And we have the boundary conditions. We have the boundary conditions which are, you know, the velocity at r equal to a is 0, that is the no slip, and we have del u over del r at r equal to 0 is 0. So, that is the symmetry boundary condition. Now, if you look at the equation, the Navier-Stokes equation, it is 0 equal to eta del square u del square u plus epsilon del square phi into delta V over L minus delta P over L. So, this equation is a linear equation, okay. So, it is a linear equation. So, we can find the solution by you know, breaking the equation into two parts and superimposing the solution, okay. So, we can say this is a linear equation so we can solve by superimposing the electroosmotic flow and the Pauli flow, okay. So, this part is going to give you the electroosmotic flow when there is no pressure gradient. Similarly, these two are going to give you the pressure driven Pauli flow, okay. So, we can write the velocity u r to be the vector summation of the Pauli plus the electroosmotic, okay. So, this is what we can write because the equation is linear. So, the two equations that we get is, one is 0 equal to eta del square u minus epsilon del square phi into delta V over L, which is nothing but the electric field, okay. And we have 0 equal to eta del square u minus delta V over L. So, we have the two equations, there is a correction here. So, 0 is eta del square u plus epsilon del square phi into del V over L, and this is for the electroosmotic flow, and this is for the pressure driven flow, which is 0 equal to eta del square u minus del P over L. So, here this equation would be solved using the condition u electroosmotic at 0 is 0 and del u EO 0 over del R is 0, and this equation will be solved based on UP A is 0 and del UP over del R are 0 equal to 0. Okay. So, we have to solve these two equations to get a solution. Now, we know the solutions for these independently. So, we can superimpose and write the expression for the velocity profile. So, the expression for the velocity profile would be for the electroosmotic flow the electroosmotic velocity profile would be UR will be 1 minus I0 lambda R over lambda d R over lambda d divided by I0 A over lambda d into epsilon xi over eta into delta V over L. So, that is the electroosmotic velocity minus A square minus R square delta P over 4 eta L. Okay. So, that is how the velocity profile for the electroosmotic flow in presence of pressure gradient is going to look like. Okay. Now, we can find the electroosmotic flow rate. So, that we will be doing in the limit of lambda d less than A. So, if you do that, we would get U Q total flow rate will be Q electroosmotic plus Q pressure driven, and we can write this pi A square into U electroosmotic, and the QP we can write this as minus delta P over R hydraulic, okay, because this is in the negative direction. We can see it here, the electroosmotic flow is going to be in this direction and the pressure driven flow is going to be in the opposite direction. So, this is going to be the QO and this is going to be the QP. So, there is a negative sign. So, you can say it is pi A square epsilon xi over eta L into delta V minus pi A4 divided by 8 eta L into delta V. So, that is the expression for the flow rate. Okay. So, next we will look at how the PQ characteristics would look like, okay, and that we will do in the subsequent class.